Welcome to the deep dive. I am so glad you're joining us today.
Yeah, thanks for having me. It's a great topic today.
It really is. Now, whether you're prepping for a major technical meeting, trying to catch up on the rapidly evolving world of Web3, or you're just insanely curious about how digital money actually moves from point A to point B without a bank in the middle, you are in the exact right place.
Absolutely. It's an ideal topic for anyone looking to move beyond, high-level blockchain buzzwords and get into the actual practical mechanics of moving digital assets.
Right. And to do that, our mission today is highly specific. We are going to demystify how to send your very first XLM payment on the Stellar blockchain.
Which is a lot more approachable than people might think.
It really is. And we're pulling our material today directly from Module 2 of the Vibe Code blockchain course.
Which is a fantastic resource.
Yeah. For those who haven't come across it, this is a guide designed for total beginners to build on Stellar. But it takes a completely modern approach called vibe coding.
Right, where you're using AI-assisted coding, specifically Claude code in this case, to build your infrastructure.
Okay, let's unpack this. Why does this matter to you? Because we're going to break down the actual step-by-step plumbing of digital finance.
Yeah, exactly.
But instead of getting bogged down in memorizing raw syntax, we're looking at how you prompt an AI to write the Node.js scripts. It allows you to focus purely on the architectural flow of the money.
Which is really where your mental energy should be going anyway. But before we get into writing scripts and passing parameters, we need to establish the environment we're working in.
Good point.
Everything we are discussing today operates entirely in a sandbox called the testnet.
Right, so no actual money at risk here.
Zero real money involved. It is a simulated environment meant for developers to experiment, build, and frankly, occasionally break things without financial consequences.
We all break things.
Oh, constantly. To interact with this sandbox, we use the official Stellar JavaScript SDK, which is the @Stellar/Stellar's SDK package in Node.js.
So the SDK is the toolkit we use to write the code locally. But how does that local code actually talk to the global blockchain? Because they have to connect somehow.
Yeah, that happens through an HTTP API layer called Horizon.
Horizon. Okay.
When you write your JavaScript code using the SDK, it sends standard HTTP requests to a Horizon server. For our sandbox, that server is horizontestnet.stellar.org.
So it's like a bridge.
Exactly. Think of Horizon as the gateway. It takes your standard web request and translates them into the specialized protocol that the underlying Stellar core nodes actually understand.
Got it. So you've got your local script, it talks to the Horizon API, and Horizon talks to the testnet. That makes perfect sense.
Yep, that's the pipeline.
So let's look at the first step the course covers, which is getting an account. Now, if I'm building a traditional web app, I just spin up a Postgres database and insert a new user row, right?
Like very standard.
But the material points out a major quirk about blockchain accounts. You cannot just generate an address and expect the network to acknowledge it exists.
Yeah, and that is a fundamental difference between a centralized database and a distributed ledger. On Stellar, generating a cryptographic key pair, a public key and a secret key, is something you do locally on your machine.
It's completely offline at that point.
Totally offline. The network has absolutely no idea you did that. For that account to officially exist, meaning the network allocates actual storage space for it in the global ledger state, it must be funded with a minimum balance of 1 XLM.
Okay, I'm trying to think of a good way to conceptualize that. It feels less like opening a bank account and more like a rate limiting mechanism.
Right.
Or a database constraint designed to prevent spam.
That is a much better way to look at it, honestly. If anyone could generate billions of empty accounts for free, malicious actors would bloat the ledger's state size almost instantly.
Because every node has to store that data.
Exactly. Every node runner in the world would have to store gigabytes of useless, empty addresses, which would just slow down the entire network.
Right.
So requiring a 1 XLM minimum reserve ensures every entry in the database has a tiny bit of economic skin in the game. It's a really elegant spam prevention mechanism. The actual operation you use to do this on the network is called create account.
But hold on, if we are in the testnet sandbox, where do we get that initial 1 XLM to bring the account to life? We can't buy testnet tokens on a crypto exchange.
No, you definitely can't. And this is where a very handy developer tool comes into play. It's an automated faucet on the testnet known as FriendBot.
FriendBot. Yeah, I saw this in the course. The vibe coding approach here is absolutely fascinating.
It really streamlines things.
You don't have to write the HTTP request manually. You simply prompt Claude code to create a Node.js script that generates a random Stellar key pair.
Right.
The script outputs your new public key, which acts as your address, and your secret key, which is basically your password. Then you just prompt the AI to have the script send a request to FriendBot with that new public key.
And FriendBot receives it and automatically drops 10,000 testnet XLM into the address.
10,000.
Yeah, it fully funds it and officially creates the account on the ledger. It streamlines the entire onboarding process for developers.
It really does. But I know the course flags something here. There is a very necessary security warning attached to this step, right?
Yes, there absolutely is. When your script generates that key pair, it saves it locally. Now, the public key is meant to be shared. That's fine.
That's your address.
Exactly. But the secret key is the cryptographic master password to those funds. The course really emphasizes that even though you are on the testnet, you have to build robust security habits right from the start.
Because practice makes perfect.
Right. You never commit a secret key to a public GitHub repository. You never hard-code it into the client side of a web application. Whoever holds the secret key has complete, irreversible control over the account.
Practice like you play. If you get sloppy with testnet keys, you are going to eventually get sloppy with mainnet keys.
Exactly.
So, moving forward, let's say we have our funded account. We're ready to build the application logic to send some of that XLM to another user.
Now we get to the fun part.
Yes. The course breaks down any Stellar payment into 4 specific sequential steps: load, build, sign, and submit.
And those 4 steps are the non-negotiable heartbeat of the network. You cannot bypass any of them.
Okay, let's start with step 1, which is load. The instructions say you have to load the sender's account data from the Horizon API before doing anything else.
Correct.
Let me play devil's advocate here for a second. If I already have my secret key and I know exactly who I want to send the money to, why am I required to pull data from the network first? Why not just construct the payment locally and fire it off?
Because you are missing a critical piece of state data required for the transaction to actually be valid.
And what's that?
Your account sequence number. Every single account on the ledger has an internal counter. If your current sequence number is 100, the very next transaction you submit must be explicitly labeled as sequence number 101.
Oh, I see. And what happens when the network processes transaction 101?
It executes the payment and then updates your account's internal counter to 101. So your next transaction must then be 102.
So it's a strictly linear progression. But why is this necessary? Like, what problem does this actually solve?
It is the primary defense against replay attacks.
Replay attacks. Okay, break that down for us.
Imagine you send a vendor 50 XLM. You sign the transaction with your secret key, making it mathematically valid.
Right.
Without sequence numbers, a malicious actor intercepting your internet traffic could simply copy that raw transaction data and broadcast it to the network a second time.
Because the math still checks out.
Exactly. The network would see a perfectly valid signature and process it again. They could just keep draining your account by replaying the exact same valid message over and over.
Wow. But with the sequence number, the first transaction is 101. The network processes it. If the attacker replays it, the network looks at the transaction, sees it's labeled 101, looks at your account, sees the counter is already at 101, and rejects it immediately.
Precisely. It's already spent. And by loading the account first, the JavaScript SDK automatically fetches your current number and handles all that incrementing logic behind the scenes so you don't have to manually track it in your code.
Okay, that makes total sense for a single user, but let me challenge that architecture for a second.
So go for it.
If I'm building an enterprise application, say I'm an exchange trying to process thousands of withdrawals simultaneously for different users, doesn't a strict linear sequence number on a single hot wallet become a massive bottleneck? Like, if transaction 102 fails, does 103 just get stuck?
That is a very astute observation. And yes, it is a known constraint in blockchain engineering. If you try to fire off thousands of transactions concurrently from a single account, you will absolutely run into sequence collisions.
So how do the big players handle it?
Complex enterprise applications usually solve this by utilizing a concept called channel accounts.
Channel accounts.
Yeah, you're essentially spinning up a pool of secondary worker accounts to handle the outgoing traffic in parallel, rather than routing everything sequentially through one single bottleneck.
That's a brilliant workaround. Okay, so we've got the sequence number. Let's move to step 2, which is build.
Right, building the transactions.
We loaded the account, now we build the transaction using a payment operation. But as you're prompting Claude Code to write this, there is a very specific instruction in the course regarding the amount.
Yes, the string requirement.
Yes. When you specify how much XLM to send, it must be passed as a text string, like the word 10, in quotes, not as a raw mathematical integer. Why on earth would a financial SDK treat money as text?
It actually traces back to how JavaScript itself handles mathematics. JavaScript uses the IE 754 standard for double precision floating point arithmetic.
Okay, what does that mean in plain English?
What that means is that the language really struggles to represent certain decimals perfectly. If you ask JavaScript to add point 1 and point 2, it doesn't just give you point 3. It often returns point 3, 0.0000000000004.
That is terrifying for a financial application.
Right. If I'm trying to send exactly point 0.3 XLM, JavaScript might silently alter the amount before the transaction is even built.
And on a blockchain, precision is mandatory.
Exactly. If the ledger expects exactly 3 million fractional units and your code sends 3 million.04, the cryptographic hashes won't match. Or you end up burning fractions of cents across millions of transactions, which creates an accounting nightmare.
That makes a lot of sense. So by passing the amount as a text string, the Stellar SDK bypasses JavaScript's native math engine entirely?
Yes, it parses the string directly into a high-precision integer format that the core network requires.
That is a subtle but critical engineering detail. And this is exactly where vibe coding shines, right? You can just tell the AI, hey, make sure to format the payment amount as a string to avoid floating point errors, and it handles the complex syntax for you.
Exactly. It abstracts it out that headache away.
Also in the build step, we have the memo field. This is an optional 28-byte text field attached to the transaction. What's the practical application of a 28-byte memo? It seems pretty small.
It is small, but it is the backbone of how centralized cryptocurrency exchanges operate on Stellar.
Really? How so?
Well, an exchange like Coinbase or Binance, they don't create a separate Stellar account for every single one of their millions of users. That would require locking up millions of XLM just to meet that 1 XLM minimum reserve we discussed earlier.
Oh, right. That would be insanely expensive.
Very. So instead, they operate one massive master account.
So when I want to deposit funds to my exchange wallet, I'm actually sending my XLM to their centralized master account.
Correct.
But then how do they know the money came from me?
They assigned you a unique numerical memo ID. When you build your transaction, you attach that memo ID to the memo field. The exchange's internal servers monitor their master account, they read the memo ID on the incoming payments, and then they credit your internal database balance accordingly.
So it functions exactly like a routing number on a bank transfer.
Exactly like a routing number.
That clears up a ton of confusion around how exchange deposits work. Okay, so step 3 is sign, and step 4 is submit. We sign the built transaction mathematically using the secret key.
Right.
But the course highlights a potential tripwire here regarding the network passphrase.
Yes, this is crucial. When you construct the signature, you have to explicitly declare which network this transaction is intended for. For the testnet, you pass the network's .testnet variable into the SDK.
Wait, why does the signature care about the network? A cryptographic signature is just math based on the secret key. Why does it need a network label at all?
It acts as environmental replay protection. The testnet and the mainnet are completely separate ledgers, but they use the exact same cryptography. If there was no network passphrase included in the mathematical hash, you could theoretically take a transaction perfectly signed and tested in the sandbox and accidentally or maliciously broadcast it to the live mainnet, where real funds are at stake.
Oh, wow. That would be a disaster.
A huge disaster. So by injecting a unique network passphrase into the signature itself, a testnet transaction becomes cryptographically invalid on the mainnet, and vice versa.
That is a phenomenal safety net. So we sign it with the testnet passphrase and we traced it to the Horizon API.
Yes.
If it is successful, Horizon returns a transaction hash. It's a 64-character hex string that serves as your permanent receipt on the global ledger.
Which you can look up anytime.
Right. Now, before we explore what happens when things fail, let's talk about fees. What is the actual cost of doing business here?
The fees are engineered to be extremely low. The base fee for a standard operation is 100 stroops.
Stroops. Okay, I assume that's the smallest unit of an XLM.
Correct. 1 XLM is divided into 10 million stroops. So a 100 stroop fee is equal to 0.000001 XLM.
0.000001. That is practically invisible. You could process 1 million transactions for fractions of a penny.
You really could.
Which is a huge departure from the massive gas fees you see on other networks. Like, sometimes you're paying $20 just to send $50.
Exactly. The low fee structure is specifically designed to enable high volume, low value use cases. Things like global remittances and micropayments, where a flat $3 network fee would completely render the business model impossible.
Okay, so we've walked through the golden path. Everything works perfectly. But in software engineering, things rarely go perfectly on the first try.
Almost never.
Right. The course has you vibe code a command line interface tool called stellarpay.js. The goal is to run it in your terminal, pass in the amount, recipient, and memo, and execute the payment.
A great practical exercise.
Let's run a few hypothetical scenarios to see how we handle errors. Suppose I spin up the CLI tool, generate a brand new public key completely offline, and immediately try to send 5XLM to it. What happens?
You will hit a 404 account not found error.
404, just like a website.
Exactly.
Yeah.
Because you only generated the key pair locally, and it hasn't received its initial 1XLM reserve yet from FriendBot, the Horizon server looks at the ledger state, sees no record of that address, and rejects the payment. The destination simply doesn't exist yet as far as the network is concerned.
Got it. Okay, scenario 2. I check my account balance. I have exactly 10 XLM. I try to send all 10 XLM to a fully funded, valid address.
That will trigger an insufficient funds error.
Even though I have 10 and I'm sending 10.
Yes, because while you have 10 XLM, you are forgetting the network constraints. You must leave behind the 1 XLM base reserve, plus a tiny fraction of a stroop to cover the transaction fee for the payment itself. You can never drain an account to absolute zero through a standard payment operation.
That makes sense. You always have to leave a little dust behind. Okay, scenario 3. I'm building a script that processes a payroll batch. It fires off 2 payments to 2 different employees in the exact same millisecond.
Oh, this is a classic. This is where you encounter a bad sequence error.
Mm-hmm.
If your script loads the sender's account from Horizon once, caches that account object locally, and then tries to build and submit both transactions simultaneously using that same cached sequence number.
Both transactions are going to have sequence number 101.
Exactly. The first one hits the network and succeeds. The network updates your counter to 101. A millisecond later, the second transaction hits the network, also labeled 101. The network sees the duplicate sequence and immediately throws a bad sequence error.
So you have to ensure your application logic properly increments that sequence number locally if you're doing batch processing rather than constantly polling Horizon.
Exactly. Or use channel accounts like we talked about.
Okay, last scenario. What if I use this CLI tool to send a testnet stablecoin, like USDC, to a friend's newly funded account?
That results in a no trust line error.
No trust line.
Yeah. Stellar natively supports issuing custom assets.
Yeah.
But to prevent people from spamming your wallet with unwanted or malicious tokens, you cannot force an asset into someone's account. The receiving account must explicitly sign a transaction authorizing a trust line for that specific asset issuer.
Oh, I like that. So if they haven't opened that trust line, the network just blocks the transfer.
It protects the user.
So as developers vibe coding this logic, we need to wrap our submit functions in try-catch blocks. When Horizon throws an error, it returns an error object that contains specific result codes. We parse those codes to tell the user exactly what went wrong.
Right, whether they need a trust line, more funds, or to wait for a sequence to clear.
Mm-hmm.
Error handling is what separates a fragile prototype from production-ready software.
Definitely. All right, let's move to the final piece of the puzzle. Verifying the work. The payment goes through. We have our 64-character hash. We want to prove it happened. The manual way is simple. You just copy the hash, go to a block explorer like Stellar Expert, and visually confirm it. But programmatically, we can use the SDK to fetch the account's history. The SDK paginates the data nicely. However, the course introduces a concept here that fundamentally changes how you build user interfaces. We are talking about server-sent events, or SSE.
This is a major architectural shift from traditional API design.
How so?
Well, in a standard REST API application, if you want to know when a payment arrives, your client application has to constantly poll the server. It basically asks, is the money here yet? Is the money here yet? Every 2 or 3 seconds.
Which sounds incredibly inefficient.
It really is. It consumes bandwidth, it uses up compute cycles on the client,
Whoa.
and it batters the Horizon server with redundant queries. It doesn't scale.
Right.
Instead, the Stellar SDK allows you to open a persistent streaming connection using server-sent events. You essentially submit a request to Horizon saying, here is my account ID, keep this HTTP connection open, do not close it. When a transaction involving this account hits the ledger, you push that event down the pipe to me immediately.
Oh, so you aren't asking for updates, you are subscribing to them.
Yes. The data flows one way, from the server to the client, asynchronously.
If we think about the real-world application of this is the magic behind modern digital finance.
Absolutely.
When you're using a mobile payment app or checking out on an e-commerce platform, you don't want to sit there refreshing the page wondering if your money arrived.
The user expectation today is instant feedback. By utilizing SSE, the moment the transaction clears the Stellar ledger, which takes about 3 to 5 seconds, Horizon pushes the event to your Node.js backend.
Which can instantly trigger an update to your front end.
Right, like a WebSocket update, instantly displaying a green checkmark for the user. It creates a seamless, real-time user experience without overwhelming your infrastructure with polling requests.
So bringing this all together, we've covered incredible ground today. We started by exploring how to generate a key pair and bring an account to life on the testnet using FriendBot.
A very busy friend bot.
Yes, we broke down the non-negotiable 4 steps: load, build, sign, and submit. We unpacked the technical rationale behind sequence numbers, handling floating point precision by using text strings, and why network passphrases prevent catastrophic mainnet accidents.
We cover a lot.
We really did. We explored the Horizon error codes you'll inevitably face. And finally, we looked at how server-sent events allow you to stream ledger activity in real time. And we did all of this while discussing how vibe coding shifts the developer's focus from writing boilerplate syntax to designing actual architectural logic.
It is a profound shift in how we build infrastructure.
It really is.
And to wrap up, I want to leave you with a thought regarding our discussion on sequence numbers earlier.
Ooh, I like where this is going.
We established that sequence numbers must increment strictly linearly. 101, then 102, then 103, to prevent replay attacks. We also touched on how this creates a bottleneck for massive parallel processing, requiring complex workarounds like channel accounts.
Right, the enterprise problem.
Consider this engineering puzzle. Is it possible to design a blockchain architecture that completely decouples sequence numbers from a strict chronological order? Could you create a system that allows simultaneous unordered batch processing from a single account without reintroducing the risk of replay attacks?
Oh, wow.
It's a fascinating problem that next-generation ledger architectures are currently trying to solve.
That is a brilliant architectural question to chew on. How do you maintain state security without forcing everything through a single file line? Well, thank you so much for joining us on this deep dive into the mechanics of the Stellar network and the future of AI-assisted vibe coding. Keep exploring, keep questioning, and until next time, happy building.